Hi there, Level 2s. We're going to move on to torque. It's part of Chapter 10, Force, Motion and Equilibrium. And in your text, housed in text, it's on page 118. So a torque is the turning effect of a force. It's also called a moment or a leverage. So you can think of things like levers that cause a torque. So what happens here is that a force is applied a certain distance from the center of mass or from the pivot point. So think of a door. When you push a door, you don't push the door right next to the pivot. You push it at the handle usually, or in the middle, which is a certain distance from the pivot. The further you are away from the pivot point, which is where the hinges are on the door, the easier it is to open the door, right? The units for torque, that should be a curly T, are Newton meters. Force measured in newtons and distance is measured in meters. If the torques about a pivot are balanced, in other words they are equal and opposite, then the object is said to be in rotational equilibrium and it won't spin. However, if the torques about a pivot are not balanced, then the object will spin in the direction of the net torque. So for example, a wrench around a bolt or a nut being forced down a certain distance from the axis of rotation will cause a turning effect of the bolt and the wrench, of course. So here's an example. If we have first a person holding the wrench at A at a distance of 10 centimeters, they apply a force of 20 newtons, the torque will be 2 Newton meters. However, if they apply a force at B, the same force, the distance is at 0.2 meters, then the force or the torque effect or the turning effect will then be double of what it was in case A. Take a look at this example. What is the resultant torque? Pause the video here and have a think. So hopefully you realize that the equilibrium, or rather the seesaw is in equilibrium. So you've got 150 times 1 meter. And on this side you've got 50 times 3 meters. So these two, one is a clockwise torque and one is an anti-clockwise torque. So the one on the left is anti-clockwise, because if this person was the only person on the seesaw, then the seesaw would go this way. It would go in an anti-clockwise direction. If this person was the only person on the seesaw, it would go down. So that's clockwise. So the clockwise and the anti-clockwise torques are in equilibrium. You want to write this down. An object is said to be at equilibrium when the net forces on the system are 0. And when the clockwise torques equal the anti-clockwise torques. Let's have a look at this example. Consider a seesaw with a 35 kilogram child 3 meters to the left of the fulcrum. And as you can see, the force applied is force due to gravity, 35 times 9.8. And then the adult on the right pushing, or has a force down of 65 times 9.8. But we're not going to look at that just yet. What we need to do is calculate the torque caused by the child. So in order to do that, we say 3 times the force. Now a lot of people tend to forget to put the 9.8 in here. So it's a 35 times 9.8, because you have to convert this to a force. So then times it by the distance. So it's in, the answer is in Newton meters, and you need to give a direction. So it's in anti-clockwise. Now a number of people tend to forget and don't understand this, but what I always say is look at the object, right, which in this case is the child. Look at what would happen if their force applied was the only force on this system. Then what would the system do? It would move anti-clockwise. It would go down on the left and up on the right. So for this object, or the child, they're going to move anti-clockwise, right? Now let's calculate the torque caused by the adult. So again, torque clockwise. Please note the subscripts. This was anti-clockwise. We're now looking at clockwise. Is going to be 65 times by 9.8 times by the 2. Now we need to work out the net or overall torque about the fulcrum. So that's what's happening in the anti-clockwise direction. Take away what's happening in the clockwise direction, and we end up with an overall net torque of 245 Newton meters clockwise. So the next question asks, where would the adult have to sit for the seesaw to be balanced? Perhaps pause here and think about how you might work that out. So in order for the seesaw to be balanced, the adult would need to move to the left of the fulcrum, right? So then the beam must be in equilibrium. What did that mean? What did we say earlier? That means that the torques anticlockwise must equal the torques clockwise. And so you write it down as an equation like this, and then you solve for the new distance. So where's the adult going to move to? And you solve for that problem, and you end up with 1.615 meters. And then round it up to two significant figures. Here's one more example. We have a door which is 40 centimeters wide. It's opened by applying a force at its very edge here of 2 newtons. So you've only got one pivot point, which is over there. And obviously, therefore, the torque is the force times the distance from the pivot. Force applied at the distance, and you end up with 0.8 Newton meters. So if the handle of the door is situated a little bit closer, in other words 10 centimeters in from the edge, then your distance to the pivot will now be 30 centimeters or 0.3 meters. The answer there is 0.6 Newton meters. Sorry, it's chopped off. So to summarize, a force applied about a pivot causes a moment or a torque. If the same force acts at a greater distance from the pivot, then the torque will be larger, and any force acting through the something does not produce a torque. So what would that answer be? If it's acting through the pivot. Right. Maybe you want to write that last sentence down. Please have a look at activity 9B in class, questions 1, 3, 6, 7, 8, 10 and 11, and see how you go with solving those.